Okay, so we were discussing phase 2 for DMVPN yesterday, and we went over to see what would trigger the spokes to initiate spoke-to-spoke tunnels. Okay, and we saw the adjacency table, how Ceph kind of uses that to take a look at those. Okay, and then I also told you that when R2 realizes that it cannot, or it does not have enough information to build the spoke-to-spoke tunnel, it then does an NHRP resolution to the NHS, which then completes that information, and then the R2 and R3, they basically talk to each other directly. So we'll look at that process in or through the debug. So I already have the debugs running here. Okay, and all we need to do is we need to come in here and initiate that traffic. Okay, and hopefully we should have our spoke-to-spoke tunnel that Gelt kind of built. Just disable the debugs once. And the first thing that we'll check is our DMVPN tunnels. So you can see this is the static tunnel that we created an entry for when we moved our spokes to being a multi-point GRE. And this is the one that has been dynamically created with R3, with the other spoke. And you can see that overlay address there, .3. Now, if you come over to our logs, we can see here it says NHRP could not map whatever the R3 overlays to an NBMA. So it basically would need to send some sort of a packet, some sort of information to the NHS. Okay, and here we can see there is an NHRP resolution message that is being sent for this destination to. So here is our resolution request. Okay, and this is the source, and we are asking the NHS for a resolution to this destination. Okay, and here we basically can see that we are telling that, hey, this is the source, this is us, 25112, and this is our source, and this is the destination, but we don't know the destination NBMA. Okay. On R1, we should see the incoming resolution request. That same information here. Okay. And then if I go down here, we should see that resolution reply that is coming in, and that's where it has the client NBMA, which is the 35113 and the client protocol. Okay, so we already had information about this. We received the information about this. This is the missing piece that we received. Okay, and it was then able to add that information to its table as well. So if you do show IP NHRP, we can actually see in here that here we have this entry, that dynamic entry. Okay. So what really happens here is, I've already explained what really happens. Right, so it realizes it does not know how to reach. It sends a resolution message. Okay, R1 forwards the resolution message. Okay, so R1 does not really respond back. Okay, even though R1 knows what the information is, but what really happens is R1 forwards that resolution request to R3. Okay, and it informs R3 who is requesting the information. Okay, so R3 will receive the information at 25.112 at 100.112 is requesting for NBMA address. Now R3 will then directly share the information with R2. Okay, he will directly share its NBMA address, the underlay address 35.113. And once R2 has that information, it can then go ahead and it will be able to build that on-demand dynamic tunnel right through the, or right to the spoke. Okay, and on R1, let me see, right. So the resolution request that was received here, you can see it forwards that resolution request. Okay, forwards that resolution request. So it is not really resolving that on its own, but it really knows where that NHC is, right? Because this is a central piece, so it knows where every spoke is. So he is the one that is going to forward it out to, for whichever spoke, whichever NHC we are trying to do the resolution. And on R3, if you're going to see, R3 will receive that resolution request. Okay, and then R3 will directly talk to 1.2 and share its information. All right, so it's R2 going to R1, the NHS, and then R1 forwarding to the destination NHC, and then both of them talking to each other then. Okay, so it does not happen. R2 goes to R1, R1 sends a response back, and then the R2 is able to communicate. That's not how it works. Okay, so that's your phase 2. Okay, and I already told you, and we already saw the implementation for the EIGRP protocol. Okay, the thing that needs to be kept in mind for EIGRP in phase 2 is it does split horizon by default. You need to give the spokes the trigger. And in this case, the trigger is the next hop. Okay, if you don't have split horizon, or if we have split horizon enabled, this here, this would point to .1. Okay, in that case, there will be no spoke-to-spoke tunnel, obviously, because from R2's perspective, if it needs to go to this spoke, it just needs to go through the hub. Okay, so when you have to enforce that spoke-to-spoke tunnel way, and when you have to put in that trigger, that's a trigger for EIGRP. You have to disable split horizon, that's one thing. And then you also have to disable the next hop self, okay, so that the R1 does not put or does not replace or does not put himself as the next hop. Okay. Right, that's clear, that makes sense.
Yeah.
Now, same thing you'll have to keep in mind when you're trying to implement ospf. Okay, so previously we did the broadcast type, again, NBMA, right? Anything non-broadcast, NBMA or NBMA multipoint are not supported with this as well. Okay, so the only options you typically have is your broadcast, all right, or you could do point-to-point and point-to-multipoint. Okay. The problem is with EIGRP, we could replace or we could disable the no IP address or no self, right? With point-to-point ospf and point-to-point and point-to-multipoint. I told you in phase 1, they do not preserve next hop. Which basically means R1 will put itself as the next hop. And there's no way for you to disable that as well with point-to-point and point-to-multipoint. So you cannot use these with DMVPN phase 2. Okay. You also cannot use NBMA or NBMA or non-broadcast multipoint. Okay. That is typically cannot be done with DMVPN at all, be it phase 1 or phase 2. So with DMVPN phase 2, all you are left with that you can really use is the broadcast network type. Because that is what does not, or which is what preserves the next hop self, okay, or the next hop IP address. And the same concept applies previously as well. This does DR and BDR election. Okay, so you would always want your R1 to become the DR, and these guys should not participate in the election. Okay, so DMVPN phase 2 kind of simplifies a lot of things if you're going to see here. Okay, just one protocol type to really worry about it. Okay, so let's come in here. Let's remove our EIGRP so that we can go ahead and do our ospf and see how it looks like. Okay, so let's come into our tunnel and we'll say IP ospf network broadcast and IP ospf the process and area 100, right? We would be advertising this network. So E0/1 interface, IP ospf 100 area 0, and then we can go into our ospf process and do a passive interface for the E0/1. Same thing here, interface tunnel 100, IP ospf network, we're going to do broadcast. Okay. Before we put in the area, we'll need to make sure that it does not participate. So IP ospf priority 0, and then we can do IP ospf 100 area 0, interface E0/1, IP ospf 100 area 0, router ospf 100, passive interface E0/1. Same thing here. ospf network broadcast, IP ospf priority 0, IP ospf 100 area 0 0/1 IP ospf 100 area 0 router ospf 100 passive interface E0/1. Okay, so we should have our ospf neighbors, both DR other, that's fine. On R2, if you take a look at the routing table, right, so there is next hop preservation. So next hop is preserved as it is. This is what allows the spoke to initiate the tunnel. Okay, so currently there are no tunnels, but when I initiate this traffic here, the tunnel gets built, and we should see that dynamic tunnel coming into play. Obviously, you should see the same output on R3 as well. All right, that's your phase 2 DMVPN, which is basically your spoke-to-spoke tunnels where the hub is basically responsible for, so it is the hub here that is actually providing or conveying the information, forwarding the information in this case. Okay, so here the decision to create the spoke-to-spoke tunnel is with the spoke itself. Okay, hub is just the intermediary, right? So it's a spoke which looks at its routing table and figures out whether it needs to create a spoke-to-spoke tunnel or not. So that's why phase 2 is spoke-to-spoke tunnels, but giving the brain or basically saying that these are spoke-initiated spoke-to-spoke tunnels. Okay, so phase 2 is an enhancement for DMVPN phase 1. Okay, where phase 1 just does strictly hub and spoke. Phase 2 takes away that, improves that, and gives the spokes the capability to decide whether a spoke-to-spoke tunnel can be done or not. Okay, now the problem with phase 2 here is, first thing, everyone is now configured with MGRE interfaces. Okay, everyone is configured with MGRE, and that is also one of the mechanisms which is kind of allowing us to do these spoke-to-spoke tunnels to n number of remote spokes without really having to make static entries or static connections. Okay, everything is dynamic here. So R2 can create dynamic tunnels with anyone out there. Okay. Another thing is, with phase 2, your routing table needs to be populated with specific prefixes for the remote spoke LANs or remote spoke network. Okay, and the next hop for these remote prefixes must point to the remote tunnel's IP address. Okay, so these are the 3 specific requirements that there are within phase 2. Okay, so it is important to understand that all 3 of these points need to be met in order for spoke-to-spoke tunnels to form in phase 2. If any of these points are missing, then obviously spoke-to-spoke tunnels cannot work. Okay. So an enhancement to this that was additionally done was phase 3. Okay, phase 3 is what you would typically implement in production. Okay.
One question here, just a
Yes.
clarification. So when spoke 2 or spoke 3 needs to communicate like spoke to spoke, when the initial traffic is initiated from the router 2, the initially it will pass through the hub.
Correct.
Correct. So once it passes the traffic to R3, then later on it is not going to pass it back to hub.
Correct.
It will be directly passing it to the hub to hub.
Right. No, spoke to spoke.
Spoke to spoke here. So once if there is any ideal time like that, once there is no traffic, then it will stop. Again, if router start the traffic, then again it will pass through the host to make the session connected.
Right. Correct.
Okay. Okay. So one
Now,
more thing, when we configure the ospf, right, we have before configuring the area, we were making the priority as 0.
right.
If there is no priority, so what is going to happen?
So if there's no priority, then your spokes will take part in the DR-BDR election.
Normal the ospf process.
Correct.
It will start the best route based on the
Right. So if
bit.
R1 becomes the DR, for example, either of them would become a BDR. Okay. So if for some reason this fails, then whatever spoke was the BR, it will be promoted to being a DR, which will not serve good for your DMVPN network. So that's why we make this as a DR, and then we make both these spokes ineligible to become either a BDR or a DR. Okay, so that even if this fails, the hub, they will not be elected to a DR, or a backup BDR will not be basically elected.
Okay, in this case, in the hub, if the hub got failed, and if the router to need to make a tunnel between the hub to hub.
Correct.
Spoke to spoke. Will it happen?
No.
No. Okay.
Okay. So if your hub fails, then obviously you cannot have resolution. Okay.
Okay.
So what we are trying to do here is we are trying to implement a single hub DMVPN topology. Okay. There are dual hub DMVPN topologies as well, where you have multiple hubs providing high availability. Right. So in production, typically, if you have a very critical deployment, if so you don't want to have a single point of failure, that's typically what you would be doing as well. Okay, having two hubs. But from the exam perspective, as long as you're not doing CCI Enterprise lab exam, you typically won't be asked about dual hub DMVPN. Okay, so from security perspective, especially from the CCNP perspective, single hub topology is what you should be comfortable with.
Okay.
All right, but yes, if you want to expand your knowledge, sure, you can. You obviously can read more about that, but yes, there are dual hub DMVPN topologies that are done to resolve that single point of failure issue.
Okay.
Okay. So now, since DMVPN Phase 2 requires the MGRE interfaces and specific routes to the spoke networks, and each of these routes need to point to their own individual spoke which owns that network, all of this needs to exist in the spoke routing table in order to trigger the spoke-to-spoke tunnel. Okay, and this sometimes can limit the scalability of DMVPN as the number of spoke sites grow. Okay, so right now we have a single spoke and there's a single route, right? So for example, we have 100 spokes. So this routing table will quickly grow to 100 routes. And if there are multiple contiguous networks behind each spoke, then that could double in number of the amount of routes. Okay, so which can affect the memory on each spoke router dedicated to storing those additional routes. Okay, and then it can also have processing overhead on the hub router. Okay, so keeping in mind these things, phase 3 was engineered to solve some of these problems with phase 2. Okay, now what phase 3 says is phase 3 still allows you to do on-demand spoke-to-spoke tunnels, but the decision making of the tunnels has been removed from the spoke and it has been now given to the hub. Okay, so phase 2 was spoke initiated, spoke to spoke tunnel, spoke looking at the routing table, ceph table, incomplete entry, does the trigger, etc. In phase 3, you don't do that. In phase 3, the hub initiates the spoke to spoke tunnels. Okay, so it's a very different approach to triggering. Okay, now within Cisco documentation, there is no real logic supporting to how this really works or how it should work or what's the processes behind it. But okay, but what I'll explain is, let's just say a very close logical explanation to, okay, this is how, or this must have been the reason why, or this is the reason why, or this is the process how it kind of works. All right, so, but you typically would not find any official Cisco documentation explaining this. Okay, so in phase 3, like I said, it takes a very different approach. Rather than having the spokes make the decision, it shifts that responsibility to the hub router. Okay, now in my opinion, the logic here is in phase 2, the first packet, the resolution packet, it anyways goes to the hub, right? So the hub is always receiving that first packet. So why not give the hub the responsibility to do the tunneling? Okay, that's really what I can think of as a logical reason why they kind of thought to move that decision making to the hub rather than the spoke. Okay, so in phase 3, there was a feature that was introduced, which is called as NHRP shortcut switching. Okay, now the basic idea behind this is using NHRP messaging, the hub can signal the spokes whenever there is a possibility of a spoke-to-spoke tunnel to be formed. Okay, so the hub or the NHRP shortcut switching gives the hub the ability through NHRP messages to tell the spoke routers whenever there is a possibility or there is a potential for a spoke-to-spoke tunnel to be formed. Okay, and I'll later on I'll show you what the NHRP shortcut really means. Okay, it's basically a new type of route. And I'm pretty sure you would never have seen that route in a routing table. Okay, if you've never worked in a DMVPN environment. Okay, it's basically going to be an NHRP shortcut route. or you can call it as an override route. Okay. Now, in this case, there's a new message that is new NHRP message that is introduced, an NHRP indication message. Okay, so we have seen NHRP registration. We have seen NHRP resolution messaging. Okay. So in this case, what happens whenever the hub router forwards a packet out of the same DMVPN tunnel interface that the packet was received on. Okay, in this case, this is NGRE, right? So whatever packet comes in here and it kind of forwards it back or forwards it out, that's, you could call this as hairpinning, okay, or U-turn traffic. Okay, so anytime this happens, the hub sends this NHRP traffic indication message. Okay, this NHRP indication message is sent towards the packet's source. And I'm kind of assuming here that R2 is trying to talk to R3. Okay, or we're trying to have this communication here directly. Okay, so when the hub receives a packet and it needs to forward it out on the same interface back out, it'll basically send an NHRP traffic indication message back to the source, or towards the source of the packet. Okay. This NHRP indication message is what will cause this spoke to trigger the NHRP resolution. Okay, so spoke will not send a resolution request for the next hop address, just like we saw in DMVPN Phase 2. Okay, it will be this NHRP indication message that it receives from the hub, which will signal the spoke that there is a better next hop available to reach the destination. So to start with, the spoke does not really know about this better next hop. Okay. So in order for you to, again, migrate the current configuration from your DMVPN Phase 2 to Phase 3, there's a very simple process that goes in. And in a moment when we'll see the logs and everything, it'll make a bit more sense as to whatever I explained, what it kind of really means. Okay, so on the hub, this is what our current situation is. Okay, so on the hub, we will enable IP NHRP redirect. Okay. And on the spokes, there is again just a single command that needs to be done. This is the current state that we are in. And we'll clean up this interface a bit as well. Oh, we already had ospf running. Okay. IP NHRP shortcut. This is on the spoke. So if you don't see a command, it would typically be a default that is running. Okay, so you can check that with all. Okay, so if it's present in shown on all, it basically means it's a default. All right, similarly, you would have it running on R3 as well. I'll just configure it just for the sake of it, but there's no real need actually. Okay, so everything remains as it is, right? You just need to have the hub or the NHS configured with IP NHRP redirect. That's really it. And your spokes with the IP NHRP shortcut. That's your phase 3 config.
So we don't need any routing for this.
We do need. So I'm removing the because I want to show you EIGRP because
Okay, okay.
with phase 3 you typically would avoid using ospf altogether. Okay, and I'll explain in a bit why. Okay, so we'll enable EIGRP here. And we'll enable on the tunnel. And then we need to broadcast 17 network. Same thing here. For this, we're going to do the 24 network. Same thing for R3. Six zero. Okay, we're learning the routes and everything, so we are good with that part. Now, like I said, in phase 3, right? If this would have been in phase 2, we would have, so on the hub, I think we already have the next hop self and everything running or configured. Okay, so that's why you see this happening. Oh, sorry. Okay, so we are receiving just this route. I can disable split horizon here, 100, no IP, split horizon EIGRP 100. Okay, so it would, there's no next hop self-preservation. There's no need for us to remove that because now it's not the spokes that are going to be doing the decision making. It's going to be the hub. So any which ways, the traffic would need to be sent to the hub, just like we had in case of phase one. Okay, the traffic goes to the hub, and it's the hub which will send an NHRP traffic indication message, because of which R2 is going to do spoke-to-spoke tunnel. So in this case, to optimize the routing table, we can also do a summary address. Like so. So from phase 2 to phase 3, you can see that we have optimized the routing table as well. I could now have hundreds of spokes, and each of my spoke does not really need to have a route pointing to that remote spoke's LAN network, whatever we are trying to reach. Okay. Now, since we have R1 set up to act as an NHRP redirect, right? This is what we are enabling here for the shortcut switching. Okay, so let's test our situation. I'll enable some logs and then I'll show you some of the outputs. Okay, so let's test this spoke 2 to spoke 3 traffic there. Let me just disable the logs. Okay, so let's try this. Let's start with R2. Okay, so nothing really here. The first packet that we see is the traffic indication. Starting with R1. So what we're trying to do is R2, looking at the routing table, it sends the packet to R1. So in this form, there is no NHRP to start with, obviously. Okay. R1 receives the packet, right? And it basically would, obviously, it will try to send, or it will try to attempt to send the packet back out of this same interface, right? So that U-turn traffic from here going all the way through here through the hub, all right? So from R1's perspective, since it's doing that, we trigger the redirect. We trigger the R1 here sending a traffic indication message. And you can see that's a source, that's a destination. Okay, so R1 realizes that it has sent the traffic, or it is trying to send the packet out the same interface on which it was received, hairpinning the traffic. So R1 sends an NHRP traffic indication message to the source IP address of the initial packet, right? So this was the source. Now it is obviously the destination because it is sending that packet back. R2 receives the traffic indication message. And now it triggers the NHRP resolution. Okay, so you can see the destination here, 36116, that's this spoke here. Okay, so it has basically sent the resolution request. R1 now receives that resolution request. R1 looks at that destination protocol field. Okay, so R1 will now perform a routing table lookup for this destination address. And it will forward this resolution request to R3. Okay, so it is sending that NHRP packet to that NBMA address 35113. R3 is going to receive that. Okay, so you can see what the source is. It's 25112, which this spoke. 100.112, which this spoke external interface. And the destination is 36116. So it's receiving the resolution request. It will now send a resolution reply. Where it will share its NBMA address. Okay, R2 is going to receive that resolution reply.
So in this, there is one point it shows, right? The source became the source protocol 100.1.1.2.
Right.
The destination protocol is 36.
That is the original packet.
Oh, original one.
Right. That is the original information when he has initiated the traffic to this destination. All right. So R3 receives all the information as it is. And then R3 includes its NBMA and its underlay address and its overlay address here in the reply. That's resolution response. Okay. So from R2's perspective, this was the initial routing table, right? Where to reach this network, it needs to go here. But now R2 knows about this new route here, that it can reach directly to this 35113 to reach this remote spoke network here. Okay, so R2 will install an NHRP shortcut route in its routing table. Okay, that's the shortcut switching method that we have. Okay, so if you look at show IP route NHRP. You can see there is a NHRP route in here in the NHRP routing table, which is saying 36110 can be reached directly via 100.113. Okay. In addition to this, and you can see that route here in the actual routing table as well. Okay, so with this, we are preventing a couple of things. Okay, there's no need to add all the remote prefixes to the routing table. Since the first packet, which initially was the resolution, first packet was always going to the hub. So why not just have that happen? That's what phase 3 did. Okay, through the routing table, the first packet will always be sent to the hub, and then the hub will notify R2 that, hey, there is a better route that you can reach that location to. Okay, here's a traffic indication message, send me a resolution. That's what it's saying. Okay, and let's see, is there a okay, and we were able to, yes, that traffic will obviously will flow. I can test it from here as well. Ping 24114, it's two-way traffic. And yeah, we'll have that NHRP route in there. So if you do show IPsef as well for the 36116, it will say what the next hop is. Okay, even though if the actual routing table here is just pointing to 100.111. Okay, but because of that NHRP route, it is kind of overriding this route here. Okay, and IPsef also, the actual forwarding engine also makes that accommodation in the actual forwarding information base, which it will use to route the packet. Okay. That's your EIGRP. You cannot use ospf here because, again, I already explained that because it is not possible to completely summarize routing information from the hub to spokes in ospf. ospf is not a suitable protocol for this design for DMVPN Phase 3. Okay, so it's typically is going to be EIGRP. All right, and since you would be using DMVPN anyways if you are in a Cisco only environment. Okay, it is a Cisco proprietary thing. DMVPN is Cisco only thing. Okay, so if you have everything running Cisco routers, to be honest, you can run DMVPN. And with that being said, you should have no issues in doing EIGRP there.
So when we have the DMVPN, then obviously there will be the phase 3 setup is there. There will be
There
no
will be
phase 1,
phase 3. Correct.
no phase 1 and phase 2.
Correct.
Okay.
Okay, so the phase 3 is the actual production implementation that you do. Okay, but you can see how it has built to how it is phase 3. Okay, so it started with phase 1 and then doing all the enhancements and everything, improvements over the previous version. That's what led to the phase 3. Okay, but it's important for you to understand phase 1, phase 2, all the different commands and everything. What do they do? What do they don't do? Okay, looking at the outputs and everything. So that is the essential part.
For this DMVPN and the router to router VPN, actually we no need of any license, right?
To implement?
Yeah.
No.
For example, why this question raises, so I have few old routers in my office. So I was trying to take it back to home, and I will doing the configuration like testing.
Right.
So that already I think that's a router don't have any license or anything.
Don't
So
really need any
don't need
licensing.
any.
Right. So from a lab perspective, we don't really need anything. Okay. If it would be in production, licenses are typically used to unlock the full potential, which typically is related to your throughput. Okay. So typically licenses are tied to that or because of that. But in the lab, since there is no requirement for you to, have maybe 1 gig or 10 gig of uplink, so there's no requirement for license.
Oh, so the license will be like only for the based on the link like 10 gig.
Typically,
Only.
yes. Or there are some additional features if you want to do, right? For example, maybe if you want to run something like Thousand Eyes. Okay, so if you want to run Thousand Eyes agent on the router, then you need to have a license for that. But in order to utilize its features the way that it is natively, right, you typically don't really need to worry about any licensing.
Okay.
All right. Any questions with respect to DMVPN?
Not that, because I yesterday gone through the previous videos, so I get some ideas. Yeah. So I think it's fine.
Okay. All right. So that's really a DMVPN. Okay. So let's break for like 15 minutes, and then we'll talk or we'll discuss. Let's see if I'll be able to talk about another, because I don't have my tablet and pen to write anything. Right. So let's take a break. Let me see what we can do, and then we'll decide what we need to do moving forward. All right.
Okay.
All right.
Yeah.